Now we're going to look at one of the most famous theorems in probability theory called Bayes' theorem. And we'll start by a quick review of total probability. We'll move to the theorem and then we'll do some examples. So here's an application where we may be interested in Bayes' theorem. Suppose I tell you there's a rare disease that has a prevalence of 1 in 1,000 in the population. There's a test for the disease, but it has a false positive rate of 5% and a false negative rate of 1%. What's the probability you test positive? That's my first question. And then let's suppose you test positive. What's the probability you have the disease? So these are two different types of questions. One of the first one here, probability of positive, is a question about a total probability. The second question is a conditional probability. It's saying I test positive. What's the probability I have the disease given I test positive? So let's start with A and think of how we could get this total probability. Let's do a recap of the law of total probability. So if I want the probability of an event E, and I have information about that event E in terms of an event F and not F, right? Then I can write this as this probability. This is saying it's the probability of E and F plus the probability of E and not F, right? And then using our law of multiplication, I get up to this form. And this lets me generalize it down below even further. If these were my little sample space and I have these other events here, F1, F2, F3, F4, I can do this same idea. Okay, so let's go back and think about this for A. So you should be able to calculate A now with a refresher of total probability. So put it on pause and see what you get. All right, so I want the probability I test positive. Just to make our life easier, instead of using P for the shorthand, because I already have P for probability, I'm just going to write out pause just to make it easy to remember what we're talking about. So by the law of total probability, so LOTP, law of total probability, I can write it like this. And already when I have it in this form, it's making me think it'd be great if I put this into a probability tree just to organize everything I know a little bit easier. You don't have to. You can pull this stuff out directly from the information above, but the probability tree is going to be useful as we work through part B of this problem as well. So let's go ahead and do it. Okay, so first I have to decide how I'm going to split up the tree. Because I have information about the probability of the disease, that 1 or 1,000, that's why I used this form of the law of total probability instead of writing probability of positive, like I could have done probability of positive here times the probability of disease given positive. I could have done that, but it doesn't help because I'm trying to figure out probability of positive. So don't do that. Okay, so starting with the tree, we're going to use disease as our first branch because that is the first total probability I have information about here. So the probability of having the disease just in the general population is 1 in 1,000. And therefore, probability of no disease has to be 1 minus that, or 0.999, because again, in these trees, you can think of each of the arrows at a given vertex need to sum to 1. Okay, now let's think about the fact that we have a false positive rate of 5%. So that means in reality, you don't have the disease, so you're in the no disease, but the test says that you do. So that means you're going to be along this branch. So that branch right there will be 5%, which means that the bottom branch is going to be 95%. So I'm just going to highlight here the data that we're getting from the actual statement up here. Okay, and then the last one's a false negative. So in that case, you do have the disease. So we're along this part of the branch, but you're testing negative. So we're going to fill in this part with 1%. So all together, those are the 3 pieces of information I was given in the problem, and given those pieces of info, I could fill in the rest of the tree. All right, so now I'm ready to go ahead and calculate this total probability by just going down the branches of positive and disease and positive and no disease, right? If I take the product of these 2 here, I'm getting this, and then I'm taking the product of these 2 here to get this term, and so I get about a 5% chance. It is just a coincidence that this number is approximately equal to this one, so coincidence that those are close. It is not at all some pattern. In general, you're going to be using this law of total probability, and so if I had changed this even slightly, it would have changed this as well. All right, so that's the first question we had, part A. Now let's look at part B. So now I want to say you test positive. What's the probability you have the disease? All right, so just for reference, I'm going to put what we already did in part A, right? All right, now in part B, I want a conditional probability. And in our last video, we defined this. If I want probability of D given positive, well, that's the same as this here. And the new step, so this is going to be basically our new jump this lesson, is that in order to get this joint probability, well, I have to go down my probability tree. So I have to go here and here, which is really the product of probability of disease times probability of positive given the disease. Okay, and putting this all together, this equation has a name. It's a famous equation. It's called Bayes' theorem, or Bayes' formula, you'll hear this called. And so let's actually now put it all together. This means that our probability of disease given that we test positive is 2%. Okay, so this might seem somewhat strange to us because this test doesn't seem to have very high failure rates. I mean, false positive of 5%, false negative of 1%. Why is it true? The probability I get that I have a disease given that I test positive is only 2%. We're going to come back to that and give you some intuition about that. But first, I want to talk more about the theorem that got us there. Okay, so Bayes' theorem states that the probability of F given E is equal to, well, it's a conditional probability. My numerator is the probability of F and E. And so using the multiplication rule, I can get to this form. So let's write this out in the 2 steps that get us to this. Probability of F given E is the probability of F and E over the probability of E. So that's the first step in the proof. And then in the second step, I'm just going to rewrite the numerator using the multiplication rule. And so then this becomes probability of E given F times probability of F. And then the third step to get to this expanded form is we're just expanding the denominator. So expand probability of E using the law of total probability. And that's how you get to this expanded form here. Okay, so where does this get us? What's huge about this whole idea and about Bayes' theorem in general is that basically I am going to be taking like a prior, this is called a prior probability here. My initial, in our example, it was your initial probability of having the disease in the general population. And then you're going to update that prior belief based on some likelihood. And that's going to get you to a posterior belief. So, or a posterior probability. So based on taking a test, right, I move from just what I thought happened in the general population to an updated probability of disease given that my test is positive. And mathematically, this is really powerful because it allows us to go from, let's say I know this conditional probability here, which is called the likelihood. I can use that along with a prior probability to get to the other conditional probability. We have names, like I was mentioning, for these terms. And so think of the prior as really being what you knew before the test. And then the likelihood is this conditional probabilities of your test result. In our case, that those likelihoods depended on our false positive and false negative rates. And now let's look a little bit closer at why 2% is not completely out of the ballpark or completely out of the realm given these numbers we started with. So we are assuming a patient's picked at random. We know that the prior probability of the disease, so there's a 0.001 chance in the population that a randomly chosen person would have the disease. Then the posterior probability, so my updated probability of the disease given a positive test, ends up being 2%. It's bigger than my prior, but it's still pretty small. So is there something wrong with the test? I mean, the error rates were low, like we said, so what's going on? All right, let's visualize this. Or maybe you have a hypothesis as to why this 2% maybe is not so out of what we could expect from a test. All right, here's one way we're going to picture it. We're doing the same question. You test positive. What's the probability you have the disease? But I'm going to break it down visually here by helping us think of if I was doing this out of 1,000 people, right? The number of people with the disease to start with was only 1. Okay, so this is the key piece, and it's what's leading us to such a small probability of actually having the disease, even after testing positive, right? It was very, very unlikely that anyone in the population had this disease, 1 in 1,000. The number of people who test positive and have the disease, again, since there's only 1 that has it, in this case, there's about 1. I'm rounding here. For the people who test positive and have the disease. Number of people who test positive and don't have the disease. So that's approximately 50 people here. In the picture, you can see those are the darker pink people. And the number of people who test positive, therefore, is going to be 51. So if we think of, okay, what is my probability of the disease given I test positive? Well, that's 1 out of 51 just because we had such a small number of people with the disease to start with. So that prior information, that prior probability is huge in terms of affecting our final answer. Let's look at what happens if you were to test negative. Let's see what's the probability you have the disease given that you test negative. We'll have the same scenario, okay? So again, out of 1,000 people, there's only now we're looking at the number of people who test negative and have the disease. All right, it is such a small number. It's less than 1. It's 0.0. It's very small, 0.01. Number of people who test negative and don't have the disease, well, that's 949, okay? And then the number who tests negative in general, 949. So the probability of having the disease given that you test negative is super, super tiny. Okay, and I'm saying approximately 0. This is not 0. I can't have exactly a probability of 0, but we're just pointing out it's very small. Okay, so then you may say, well, why even test at all? This seems crazy. Well, I want you to realize what we started out with before we tested is you had a 1 in 1,000 chance of having the disease. Now when you take the test and the results are positive, well, now you know you have a 0.02 chance of having the disease. If you take the test and the results are negative, you now know you have a 0.00001% chance, or 0.00001 chance of having the disease, not percents. These are just the straight up chances. So it's still important. It's updated your initial information, and now you can be very, very confident that it's super unlikely you have the disease. And here you might be worried, but maybe not so much because, again, the chance that you had it to start with was very small. Now, I'm going to point out that the assumptions that go into this matter. In particular, we assumed a patient was just picked at random. In reality, people usually aren't picked at random for medical tests. They're expensive, they're time intensive. So usually there's some reason that your doctor is going to, suggest that you have a test. So this does make sense for a randomly picked patient because the disease is very rare. But let's say your doctor has more information before you get before you take the test. Maybe you are in a subpopulation that's genetically predisposed to have a higher chance of getting this disease. So maybe based on some other information about your medical history, let's say the doctor believes there's actually a 10% chance you have the disease. This is before you take any test. This is just based on some other info. Okay, so now imagine, based on additional information, you're in a subpopulation where there's actually a 10% chance you have the disease. You test positive. Now, what's the probability you have the disease? Okay, so now, out of my 1,000 people, 100 of them actually have the disease. So those are my blue people. Number of people who test positive and have the disease, 99 out of 100. So number of people who test positive and don't have the disease, 45. So those are my dark pink people. And therefore, number of people who test positive altogether, 99 plus 45. So that's my dark blue plus the dark pink in the picture. This one light blue right here was the one who did not test positive but had the disease, right? Because I had 100 people with the disease and 99 of them tested positive. Okay. And so altogether, I can see my probability of having the disease, given that I'm positive, is around 69%. So that was a big update from what my doctor previously thought. So again, now notice all I'm doing in this problem was just changing the prior probability. If you have a 10% chance of having the disease, I take the test. I now have a 69% chance of having the disease if my test is positive. And if my test is negative, I now only have a 0.1% chance of having the disease. I can feel very rest assured that I likely don't have it. So this is just showing the impact of your assumptions and your original prior probability on what the output of these tests will be, because I didn't change the accuracy of the tests. So this leads us to, how do we decide that prior probability? And this leads us back to the two different branches, or two different ways we can define probabilities. There's the frequentist view, which is the frequency with which something would occur in repeated trials. If it's possible to do that or to estimate that, that's great. But there's also a lot of situations where we can't do that. And for example, your doctor may just be looking at based on their own experience or other information they've seen. There's some subjective degree of belief that you may have a higher likelihood or a higher chance of having the disease. So why would we use something like a subjective prior, like we did with the doctor example? That's just a way to quantify uncertainty about an outcome when you don't have the ability to do this type of limit as you redo the trial over and over. There's lots of situations like that, especially rare events where we don't have really any data or ability to be able to do the frequentist view to come up with the probability. And so in that case, having a Bayesian perspective is very useful. All right, let's try one more example. So notice that I can calculate how many existing spam emails contain, for example, the word dear. But now what if I wanted to create a spam filter so that I could calculate the probability that an email is spam given that it contains, for example, the word dear? All right, so here's some made up data. Let's suppose that I take a list of all the email that I get in 2016 and I classify it, and I find that 60% of it was spam. And then I look within and see out of the spam emails, 20% has the word dear, 1% of my non-spam has the word dear. And now I want to know, what's the probability that an email with the word dear is actually spam? So take a minute, see if you can do these 3 steps where you define your events, you state your goal, identify the known probabilities, and then we solve. All right, so let's let E be the event E be that the email contains dear, the event F be that the email is spam. We're looking for the probability of spam given dear. And then let's translate these 3 things that were given here into math probability terms. And so notice the top one is just the probability of getting spam, so probability of F. This is the probability of E given F, and this is the probability of E given not F. Oh, this should say this has the word dear. Okay, so those are my known probabilities. This is what I want to calculate. And so this is a classic example of where I could use Bayes, because when I go to solve, I want probability of F given E, and I don't know it, but I do know probability of E given F. Okay, so I'm going to write this. This is probability of E given F times the probability of F, and then divided by probability of E, but we can use law of total probability to help us get that. To make our life a little bit simpler, I'm also just going to draw the tree here. You don't have to, but just another way of visualizing. So probability of F we had above was 0.6. So probability of not F is 0.4. And then let's do both of these ideas here. So let's make this be spam right here. And then we're going to let this say dear here and no dear. Dear and no dear. Okay, and well, this one will be ham. Okay, so the probability of E given F I have above is 0.2. That was one of my given pieces of info up here. And then I'm just going to fill out the ones I need to get to probability of E, because that's in my denominator. So I'm going to come back over here. This is probability of E given not F. And that was also given to me, 0.01. So I actually don't even have to fill out the other parts of the tree here if I don't want to, because I'm just going to be following along the branches here and here, and then this branch here and here in order to get my denominator. Okay, so this is now going to be probability, I'm going to put it all together. So this is going to be 0.6 times 0.2. That's getting me down my first branch. And then the second branch is going to be 0.4 times 0.01. That's law of total probability. And my numerator is this 0.6 times this 0.2 times 0.2 here. Good. And so we can put this all together and we get approximately 0.967. So our answer was closest to D. And again, classic example of using Bayes. Okay, our last discussion question I want you to think about is, suppose I tell you that a car heading from Berkeley to San Francisco is pulled over on the freeway for speeding. Which type of car is it more likely to be, in your data scientist opinion? A Tesla, which is relatively common in California, or a Lamborghini, which is rare and known for speeding? Just a heads up, you don't have enough information to calculate the answer directly, but what would you guess and why? Make some reasonable assumptions. All right, so what would you guess and why? All right, my thought process is I'm looking for the probability it's Tesla given it's speeding versus the probability it's a Lamborghini given that it's speeding. Okay, and so if I use Bayes, right, the probability of a Tesla given it's speeding, well, my denominator is going to be probability of speeding, but that's going to be true over here too. So really the numerator is going to be the difference. And this will be probability of speeding given Tesla times probability of Tesla. This will be probability of speeding given Lamborghini times probability of Lamborghini. So this is Bayes here in both of these situations. Okay, so I'm going to say this versus this. So I'm just going to compare the numerators because the denominators have the same scale. One thing we're going to notice is Lamborghinis are relatively rare. So this number is going to be very small right here. Okay, and this number is going to be much, much larger. So we're going to say probability of T is much, much larger than probability of L. Now, the probability it's speeding given it's Tesla versus speeding given it's Lamborghini. Okay, let's say that this probability is bigger. That's fine. I'm going to say that's bigger than this one. I don't think that that probability can be so much larger to compensate for the fact that Lamborghinis are much less rare or much less common than Teslas. So if I think about like what's going to win out in this, what's going to be driving this numerator here is the fact that this is so small. Just like what we saw in that 1 in 1,000 chance of having the disease was really driving the whole process. So yes, even though this quantity here might be a little bit bigger than this quantity here, it's not going to be enough to make up for the fact that this is so much smaller than this. So I'm going to argue that, let me erase this here, that it's going to be more likely that it was a Tesla. Even though Lamborghinis are known for speeding, there's just so many more Teslas. It's much more likely that I would have seen a Tesla than a Lamborghini. That's my reasoning in this. So these are just some examples of how to apply Bayes' theorem and where this type of reasoning will come into play.